It's not too clear how it relates to what I do for a living. So I'll try to explain that. But first, let me thank Nidhi, Fabian, and Philippe for tolerating my visit here for now what's almost 3 days, 2.5 days. And thank you. It's always a pleasure to come here. And today I can see the weather is improving also on the eve of my departure, which is also a good thing. So today's talk is about Future X. Those of us who work at Bell Labs have heard this phrase Future X a lot. So it comes from an initiative by Marcus Weldon, who actually is the co-author of this paper, this work, where he started writing a bunch of documents about the future of wireless, future of broadband access, future of all aspects of information and communication technologies. So there's a book that he and the senior leadership team of Bell Labs put together, came out 2 years ago. I think some of us have this book on our bookshelves. We're supposed to anyway, even if you haven't read it. It's supposed to be there. Anyway, the idea is to project and see where we are going. It's a roadmap and also part of our vision. And so that's the Future X vision part. And then this growth paradox came about as a result of a book review that I read. And as I was reading the book review, it seemed to be essentially the opposite of what Marcus was telling us. So I'll tell you about the book in a minute. So it was almost as if somebody had taken the Future X vision, turned it upside down, and was giving us an anti-vision of technology. So that was quite intriguing. So I actually ended up reading the book. And then as a result of that, I had conversations with Marcus and then with our business modeling team in Bell Labs, Sanjay Kamat, Subra Prakash, and Gina Shi were involved in getting a lot of the data. This is a very data-oriented effort, project. I'll tell you how much math there is in it. It's not a lot, but the math is interesting. It's implicit, but also instructive for mathematicians to see how mathematical models qualitatively get into some interesting discussions, in this case about the future of technology. So that's the introduction. By the way, feel free to stop me, ask questions if something needs clarification. So I wasn't aware of this debate, particularly with this incident of reading a review of Robert Gordon's book and then hearing Marcus Weldon talk about Future X has made me aware that there is some debate going on between what's called technology pessimists and technology optimists. Technology pessimists think that the great age of economic growth is behind us, despite all the great things that we have invented in the past 50 years. And some of those economic miracles that we saw in the 19th century and the 20th century were one-time events, and that's behind us, roughly. That's what they say. Technology optimists, Brynjolfsson and Kurzweil, amongst them, believe that no, the opposite is true. The technology is taking us to some uncharted territory, fascinating landscape with enormous potential for economic growth. So it's not hard to see that these camps have a difference of opinion. What is interesting is to see what is the methodology, why they are saying what they're saying beyond science fiction and imagination. Is there a scientific basis for either point? So this work, in some sense, attempts to put some meat into this argument. And you can judge whether we have gone far enough or whether it's too preliminary. So clearly, Future X book that Marcus and his team at Bell Labs put together belongs to the second category. So that's why Robert Gordon's book, which actually gave rise to this discussion, was interesting and instructive to guide us to articulate this position of techno-optimists a little better. So let me give you a little bit of math requirements for this work, which is very modest. So essentially, this talk is about this curve. And you come across this curve in all kinds of places. Most recently, layers of neural nets have this trigger function. If the aggregate flow from various previous layers reach a certain value in this curve, then the neuron activates. People who look at marketing material, they've seen this curve as diffusion curve. When you have an invention, if it's a successful invention, it slowly grows almost imperceptibly in the early stages. And then all of a sudden there is a rise, and then there is massive adoption. Okay? So of course the slope of the curve at the inflection point determines the speed of the phase transition. But that's as much math there is in this talk. But the way we come to this is in percolation, you have a process, some kind of innovation. It starts with some adoption, then the density increases, and the density increases more until you have universal adoption. And if you look at the mean field approach to this, meaning take the average number of people over time, then you see a curve, the famous SCurve. So you can think of this as the adoption, very little evidence, fast growth, and then ultimate penetration to the maximum possible level. And it's interesting that this is natural. We see it in all kinds of phenomena, physics, chemistry, but also in economics. But you look at the literature about growth, everybody assumes linear growth, 2% a year. And we look at the internet, did it affect our productivity? Look at the past 10 years, we see nothing. And people conclude all sorts of things from this observation. What this curve is telling us is that these processes don't follow a linear pattern at all. In fact, in the early stages, it's very hard to see anything. And then all of a sudden, there is this sudden shift, this phase transition. And I think this is at the bottom of our explanation of this techno-optimism camp. Of course, in reality, data is never nice and smooth. The data that one collects after enough processing looks something like this. And as we all of us who have messed around with data know that there's a curve fitting exercise. You find the best innovation curve that describes this. And this particular one is the adjusted productivity per hour in India from 1950 to 2015. So you can decide whether this follows a sigmoid function or not. It does. The error is pretty small, but of course you have these occasional signals, noise. And people misunderstand these often, even experts. They say, oh, 1970, there's some amazing thing happening in India. But the amazing thing is not what's happening or what has been happening the past few years. The amazing thing is what the large-scale feature of this signal is, which is something macroscopic is happening globally. Okay, so let's get back to the beginning of the story, which is this book that was published in the first quarter of 2016. Robert Gordon. It's entitled The Rise and Fall of American Growth. And essentially, the book is about the productivity miracle that was observed in the US in the 1940s and early 50s. Okay? And people have given all kinds of explanations to them. Robert Gordon's position is that this productivity growth was due to some amazing set of technological inventions. The car, the plane, road transportation networks, electricity grids, gas networks. He actually lists a lot of infrastructure technologies that contributed to this, but also consumer electronics, the kitchen appliances, the consumer credit. He even has a chapter on fashion and whatnot. And essentially, the argument is based on this chart of his on the left-hand side. It looks at the growth. Think of this as concretely, suppose one person, a worker, produces one chair every day in 1870, and you want to see 100 years later, one person, one worker produces how many chairs in 1970. So that factor is the growth. It's a multiplicative factor. So usually the y-axis is a logarithmic scale because there is a constant growth always as part of the story here. So you talk about the US economy growing at the rate of 1.7% a year, and everybody wants to push it to be 1.9%. Now China has been growing at 6% a year, a massive, amazing number, and people are wondering why it is slowing down. Are they not selling enough cars or enough electronics to the rest of the world? So on the left-hand side, Gordon's observation. So this is the cumulative, and then on the right-hand side, I have the growth per decade. As you can see, this is incremental. And the key thing is you have this dip, 1930s, this is the Depression, and then you have post-World War II. However, I mean, these things are these big noises, big interruptions, but the reality is that even if there was no depression, this jump is huge. Yeah, over 35% in a decade, unheard of, and that's what he's talking about. And that gave rise to 50 years of prosperity with implications all around the world. Yes?
Just a question on this graph. So it is the growth for the country, for the United States?
Just for the United States, yeah.
And what is the growth in population? Because I think, in my opinion, the right figure is per person. Because
yes, there are two charts here. One of them, the black one, is the output per person. The black one is output per hour, and the white one is the output per person.
Okay.
Yeah, so that one is also jumping. Or no matter how you do.
I just look at the right in that.
No, that's a good question, and one you often wonders whether they're measuring the right thing, given the population is growing. Is that fair? And no matter how you do this, you see this jump.
There's unemployment that has kind of amplified the effect of lower productivity per person and fewer people employed in the world.
Well, the per hour is net of that.
Okay. The right is per hour.
Yeah, the left-hand side has both per hour. On the right-hand side, I'm just showing it for... what is it showing? It doesn't say. It's one or the other. But it's no matter which one you take, it's the same story. The numbers may be a little different.
It's just productivity, but usually productivity is...
Per person or per hour?
I think it's, I don't know if it's per person.
That's the question.
It usually factors in the population.
One hopes.
Working population.
The working population. But still, I mean, yeah, I think you can take the limit and say, what if you have an amazing technology that makes one person work and everybody else is at home? So productivity increases, and yet the rest of the population is unemployed. There's none of that. That trick is not being used here. It's a fair... So anyway, I mean, there's the way to think about this chart, at least a mathematician's way of thinking about this chart, or to be specific, my way, is to see this as three segments. There is a red segment from 1890, yeah, 1890 to right up to 1940. Of course, the Great Depression per hour productivity is really low, but so that's a linear segment. There's a jump, and then there's an upper segment. The slope is essentially the same, and that's the slope that we've been talking about forever, a 2% growth, which is common in the Western economies. Essentially, you have that given. So given that the y-axis is a log scale, you have to be careful how this is working. There is, when you have 2%, if the bank is giving you 2% interest, the accumulation grows ultimately exponentially, but we have a jump in this exponential growth, if you like. So one has to factor that in. So let me summarize what the book is saying. If you have time, it's worth looking at it because it's very well written. It's easy to follow it. There's not much jargon. So the claim one of the book is that great inventions are invented once. So once an invention has its impact, there is a jump, and then we all assume it's there. Once you have an electric kettle, you can boil water in a minute, and that's it. 15 minutes boiling on a gas stove is reduced by a factor of 10, and now that's factored in. There is no jump until you have maybe a nuclear kettle, which boils water in 30 seconds or 3 seconds, okay? So that's the argument. So he says great inventions, 19th century, specifically the period 1850 to 1950 was that period of great inventions. And he says something about GDP that my business modeling people understand. I'm not going to try to go over it. It doesn't change the argument. But it's something to do about how we measure GDP, gross domestic product. And yeah, I think it's designed for 19th century or early 20th century economies. And the internet by itself is hard to capture in the way it influences GDP. Then claim 3, it's an interesting observation because his claim 3 was really the clue that gave us some argument, some plausible argument that maybe there's something more going on here than what Gordon himself, but it's in his book. He talks about decades for invention to have their full impact. Remember that SCurve, early phases they don't look like there's anything going on. And then claim 4, another piece is about infrastructure. What was the big deal about early 20th century was the development of these massive infrastructures, transportation, electricity grid, or energy grid, electricity and gas. You have water and sanitation, and communication, of course, telephony. Depending, okay? And then you have these exogenous factors like Great Depression, World War II, which massive stochastic noise coming into this equation. And then there is claim 6, which is really the odd piece. Then Gordon actually does go into the 1980s and then 1990s, 2000, and he says, look at the figures, growth figures. We had this great invention, the internet, World Wide Web. As researchers, we know that it used to take us 4 or 5 days to get the full set of references that we wanted to read. You had to go to the library, ask for a copy. At best half a day, sometimes a day or two later, you will have. Today, downloading a copy of the papers that we want to read in preparation for some work, the whole thing is less than a minute. So where is this productivity gain? It's missing. It's not there. Well, why? Because it doesn't affect GDP. It hasn't had any impact on economic growth. That's what he says. And it's true. It's not there. You look at all these numbers, somehow the Internet World Wide Web has not increased productivity in any significant amount. So from that, Gordon concludes that maybe the Internet, the World Wide Web were not such great inventions. They're not as good as planes and cars and electric grid.
But why would you say that? Maybe there was...
I wouldn't say that.
Why would
Gordon does.
whoever would
I'm trying to say the opposite.
Okay, sorry, then go on.
Yes, that's right. But carry on. Assume that I'm the devil's advocate.
Okay, so maybe there's no increase in productivity seen because there was a decrease due to something else, and there was an increase due to the information technology. Like manufacturing went down, but information technology took over. So overall, you have still the same productivity.
Right, and that's a fair question, and I'm sure there are lots of economics PhD students who have worked on this. Say, was the reduction in productivity why the internet's amazing increase in productivity was zeroed out? I don't know the answer to that. But I think we have an explanation which doesn't require any negatives. So that's this.
Also, there are impacts that are not measurable through the productivity.
Yes.
Look at the people in the street. Their use of mobile phone or internet is totally different since along the years. In the 90s, it wasn't the same in today.
Yeah. So actually, Gordon does talk about that.
They don't produce.
Yes.
They don't produce.
That's you hit it on the head.
The question is how does it change the society?
Okay, so Gordon actually takes, in one of his chapters, he says, look at the smartphones, what have they done? They have brought movies to the teenagers, and so that productivity didn't increase, you just waste more time. So in fact, if anything, we have decreased productivity because instead of doing homework, they're watching movies on their cell phone. But I think that's silly. I mean, time is wasted thanks to new technology, but I don't think that's really the reason why things the way they are.
Yeah, but something relevant to what you say is also basically that, I don't know, see for example how much has increased the average number of PhDs per country.
That's productivity of the academics.
Exactly.
But that doesn't increase the GDP.
Yes, that's what I'm saying. So the problem is basically...
Philippe is raising his hand as an example. Yes. Yeah, you're right. I think there is also a component of this is we don't know how to measure productivity. In one of the slides I had it. The techno-pessimists have all the metrics because the metrics that we have developed work for their argument. But the optimists have not defined new measures. How do you factor in the fact that from 3 days to get papers for our research, you have reduced that phase to less than 5 minutes? That productivity is a couple of orders of magnitude. How do we measure that? And how does it affect the whole macroeconomic picture?
Isn't it also just referring to your question that we get a lot more book also?
A lot more?
Book, extra papers that we don't really need. So
Oh, yes.
I'm just thinking whenever
Yes, so this is productivity in a negative way. We are producing, so imagine we were producing thousands of chairs a day. Well, there's only so many chairs that people need. So these chairs are not doing anything. So you're right, but I think the conclusion here is that we need the right metric, and maybe the right metrics we don't have. But I'm going to try to convince you that even with the wrong metrics, maybe there's an explanation. How am I doing, by the way? What's the time?
About 20 minutes.
Oh, okay. Okay, so that.
We started late, so...
Oh, okay. Well, I think 20 minutes should be enough. So the Gordon argument. Okay. So you saw this curve before. I showed you the way to think about it. Break it up into two components with essentially equal slope, and see what this jump is. At least numerically detected. It's there. And again, we looked at this earlier. This is per decade, by the way. This is National Bureau of what is it? National Bureau of Labor Statistics. Okay. So, so the first thing is to fit a line 1, 2, 3, 4, 5, 6, 7 to the first. So we want to detect the original trend. We don't want to treat what happens around here to just get an approximate trend, but we want to see this earlier trend and then the later trend. So we fit a curve, and that's your 1.7 annual return, annual growth that we talked about. So now take that out. So we call, let's call this adjusted productivity. This is as if you didn't have that 1.7 to 2% growth annually. Okay? So what does this look like? So with the introduction I gave you, you should be convinced that this is really part of an S-curve. There is something going on that is captured in the growth data. We don't know what it is, but something caused this jump, and you can fit, and it's not a bad fit despite the appearances. It has the high level features are there. The flattening, there's a dip because of the depression, and this is usually the tipping point around here. This is where you begin to feel that something has happened. The smartphones were not popular, and then all of a sudden everybody in the street had one. So if we do it this way, we can detect we can actually now approximate this entire time series with one smooth curve, and that curve is essentially a linear segment, an S-curve followed by another linear segment with the same slope, and the inflection point of that is around 1950. So that's essentially right. That's when this productivity jump occurred. So we have some analytical expression. We don't know what that is, but we have a good fit because the numbers that it shows look right. So this point is the inflection point. That's the tipping point, year being around 1951. If we had, the correct way of doing this was to look at the annual growth, not the per decade average. The reason was that I didn't know where to go to look for the annual growth. My first approximation was a Google search. The National Bureau of Labor Statistics had these by decade, so I used them. And then later on, my business modeling colleagues got the actual data per year. Okay, so now let's go back to the counter-argument of Gordon. He talks about these particularly infrastructure technologies that are networked. The word networked is very powerful. It gives you this ability to bring things closer together. If you have a bunch of villages, interaction is limited. Once you have a road or roads between them, there is more interaction. So this is understood in the economic literature that infrastructure reduce distances. They stimulate interaction. So if you take at these very same infrastructure technologies that Gordon introduces in his book, which is electricity, gas, water, sanitation, transportation, and phone, and look at the diffusion of these. Now this is the percolation model that we talked about. These are infrastructure, and then on top of this there is what happens, economic activity. And look at how they have spread across the landscape from 1900 to 1980. And you can look at the average. So the reason I looked at the average is because I wanted a simple model. If you want to have growth as a function of these infrastructure technologies, each one with a different coefficient, you have to do a lot more number crunching than I was willing to do. So I just took their average. Average penetration, this is the percentage of households that have electricity or gas as a function of time. So you can see again, the average does have the kind of shape that we were talking about. It has a bump here and there, but overall there is flatness, nothing happening, although roads were being built during these times, and electricity grid was being formed. But then you have this, the jump, the middle part is what usually is interesting. It's about 10, 20 years long. So, and now this is a model based on correlation, not based on actual causation. Now what we can do is take the growth, which was a function of time. We have the diffusion of these technologies, which is as a function of time, and then eliminate time. So you create a function of growth, which relates growth to diffusion of these technologies. So this is a man-made construct we're trying to explain. So we get, again, this curve, which says when the penetration of these key technologies exceeded 50%, it just happened to be 51, but I'm sure that's just a fluke. The reality is it's somewhere between 50 to 60%. So the claim is, therefore, that these key infrastructure technologies, as they diffuse, they stimulate activity, they stimulate productivity, and then you have this growth spurt, which is observable at the inflection point, and that's around, again, 1951 at 51%. Okay, so this is a claim. So I decided to see whether there is actual truth in this diffusion. Does it happen like that? So I found this book. It's earlier, from 1990. Grubler is the author, and it has a similar title, The Rise and Fall of Infrastructure, it's called. Gordon's book is called The Rise and Fall of American Growth. He doesn't reference this book, so I don't know if they're aware of each other's work. But he essentially works with this sigmoid function. It comes from, you've seen it in multiple contexts, like the growth of an innovation in the early phases is exponential because you're far away from the saturation point. The rate of change is proportional to the population. As you approach the saturation point, the dominant factor becomes the negative part, so it flattens out. Okay, and then he talks about this, the inflection point, this, you can characterize this delta time is the span between 10% penetration and 90%. So that gives you, it's kind of a signature of an innovation. How long does it take to penetration to go from 10% to 90%? So he talks about these things. So there are really essentially three phases. The initial slow phase, where it's almost invisible. So where smartphones, great things, we don't know. Some people have it, some people don't have it. And this continues sometimes for a while until all of a sudden, before you know it, every one of your friends has it. And then at the end, it's done. It's become adopted completely. Yeah.
Why do you say that for the initial growth, for me, it is exponential?
Well, if you look at it is exponential. You can't see it.
It is small, of course, because it starts very low, but it is exponential, and then it is almost linear.
Well, it's linear in this phase, around here.
Yeah.
But that's a mistake to think that things will grow at that rate. That's the maximum growth rate.
You reach the saturation.
Yeah, the inflection point is where you see the maximum rate of adoption. Okay? But I think this is where people get misled. This is the phase where nothing seems to be happening, and then all of a sudden you see this rise, which now looks like exponential. Okay, so he looks at data. This is railways in the US in the 19th century. Very good fit. Then he does this trick, because fitting SCurves is hard. At least in 1990s it was harder. It's easier now. There is lots of good Python packages. But if you do the log of y-axis over the saturation minus y-axis, it turns out you get a linear curve. So if you do the graphs, if you make the y-axis to be log of y over k minus y, then it's much easier to see, to test the theory of this S shape. All you have to do is draw these linear charts, and Grubler has a whole bunch of these transportation canals in the UK in the 18th century. And then you have steamships in the 19th century, railway miles worldwide. He has a few of these S-curves too. This is road miles in the US, road miles in USSR. So the point is that, yeah, these curves are not just an idealization. They are being tested by practicing economists. So essentially our model, the claim is as follows, that you have these key technologies, the infrastructure networked, so they have the maximum impact on daily life, like train, roads, planes, steamships. Then you have communication, water, sanitation, electric grids. Each one of these is an S-curve. The economy is a combination of these, and that combination itself, the growth is a function of these. So the same way, so how do you explain the fact that internet didn't have an impact on productivity? Well, this is like saying electricity did not by itself create the economic growth in the US. It didn't. That's because electricity by itself is not enough. It's just one of the many constituent elements, right? So internet is one component here. So how do we test this hypothesis? Well, it's hard to test this hypothesis because then you have to have a simulated economy that runs for 100 years, and then you can see if it's true. But then what's the assumptions? And okay, so let's see. I think we have summarized this already. The network effect. So let's, before we do any more justification of the model, let's extrapolate from it. So the internet and World Wide Web by itself, by themselves, are not adequate. So what are the other constituents? What are the other infrastructure technologies that combination with World Wide Web are going to give us a productivity boost? So this is, there's more, of course, there's a lot more speculation here now. Yes, maybe it's for buy Nokia. That's the answer. So this is primarily physical before. Now we've gone past the physical. The entire Gordon model is based on physical infrastructure. If you think about water, sanitation, electric grid, transportation, communication, well, that one, telephony, was the beginning. So here, instead of, we have digital version of these. We have the evolution of the things that were done physically are now done digitally. Meetings, a lot of our meetings are now done over the internet. So the claim is that there is a correspondence on the emerging digital world, which consists of what? Let's see if, so communication, telephony in Gordon's model will have the information. We have the way it reaches our homes is through broadband. Energy, gas and electricity, you have the new digital energy, which is controllable grid, smart grid as you call it. You can control it in your home. You can decide when you charge things, when the prices are renewable energy. Transportation, trains, cars, roads. In the physical world, you have autonomous vehicles. People are talking about, driven by AI. Health and sanitation, water, sewer. You have digital health. These are wearables. They are constantly being monitored all day, and therefore that should affect how one's health is observed, and therefore result in longevity or reduction in cost. A lot of the cost in health is due to missing diagnostics in time. And then we have digital and cognitive technologies in manufacturing, which is new. You know, digital printers are the giant version of those. Those are thought to be the next generation of factories. You don't actually have. They have equipment that, if you look at how the latest chips are manufactured, it's an example of the components are themselves built by digital printers that are printing components of the next generation of the factory. So here is what my business modeling colleagues are good at. So they extrapolated the data. They came out with some diffusion curves for these new digital technologies. And I really can't comment. They know how to do this. Obviously, you need to be good at something to decide how much adoption of 3D printers there are in 2025 and things like that.
When you have mentioned that, but because we have a measurable impact of electronics, which is, I would say, the ancestor of our digital world, the impact of electronics has been huge. For example, the car contains much more electronics than the lunar module had when it landed on the moon. And it had an impact. The consumption of gas has been divided by 4, 5, maybe sometimes 10 compared to American cars.
Right.
And now it is everywhere. The physical infrastructure has grown because of the electronic impact of the electronic equipment, which reduce car consumption, reduce the cost of the car, and also the old plane.
Right.
Fly, I don't know, one plane can take off every minute in an airport. This could not be done without electronic. This has an impact, and it's measurable, even on the physical. So I think I can expect something measurable too for the digital evolution.
Yes.
For me, which is just the continuation of the electronic.
No, I agree. I mean, there's no question. Look at this device is more powerful than computers in the 60s, so there's been massive, super exponential growth here. The question that Gordon asked is not the amazing processing power. The question is how the
physical growth of the infrastructure. I can take exactly the.
But how does it overall?
Which was about the physical infrastructure, which we could discuss, but let's take it as an example. The traffic of cars has been increased by a factor of 100,000 since the beginning of the century.
And that's a good thing?
I am not saying that the growth is a good thing, by the way. That's very about that. I just say that it has a global impact.
Oh, so to be precise, I mean...
It's amazing. It's just,
right.
When you drive your car, you are not amazed by your car. You drive it.
You're right. And as I said, I think we have to capture this in a new measure of productivity. But Gordon is primarily concerned on productivity that is observable in terms of how you measure GDP.
Yes, and this is measurable. The impact is measurable. You can see that.
On the GDP?
More cars, if the car were consuming 50 liters per 100 kilometers as they was doing in the 50s, sure, you could not have a lot of cars on the road. That's true. That has an impact.
Yeah, but I mean, if you write the increase in the speed of computing, and if you look at the growth per year, you don't see a correlation. One has been growing exponentially, and the other one has stayed at 1.8% on average a year.
There's a limit on the impact of the physical structure. The impact of the physical structure is not going to expand the structure.
Yeah, I mean, I agree with you that something is missing in the way we measure it, but ultimately Gordon has a point in terms of, you know, look at the compensation, look at all these metrics that measure economic activity have been more or less stagnant compared to what we saw in the period 1940 to 1950. Anyway, so I want to skip this, but I just want to give you a prediction. So if you now aggregate these and average them, at what point do we get this 50 to 60% penetration of these digital technologies? Turns out to be somewhere in the 2030s. So that's a prediction. If you can find me in the 2030s, and if this hasn't happened, then I owe you something. So that's a bet. But before I finish, let me just show you one other chart that is interesting. So how do you test a hypothesis like this? When you can't simulate growth? Well, you can look at other countries, right? So what do they? So two good examples would be China and India, right? So my colleagues got numbers for China and India. So this is the output per hour, not per person. In China, again, so this is not a log scale y-axis, that's why you see the exponential. But you take the exponential, you again fit the linear to the early phase. The early phase from 1950 to 1980. And then you do see, and again, you have the flat part, you have a growth which started in the 1990s, and then the flattening that has happened since 2010. Does that sound familiar? All these stuff we read in China about the slowdown of economic growth, are they doing anything wrong? Maybe not. They are in the tail part of the S-curve. What do you expect? Oh, yes.
I mean, the 90s is basically the end of the Soviet Union, or for example...
Do you think that affected Chinese productivity?
Of course, because in my opinion, the correlation is clear because as the model of basic mother communism failed, I think that this liberated somehow the nowadays Chinese capitalism to take accepted.
Yeah, I don't know. I mean, you're right, but what can we do? Either we can do no mathematics or numerical modeling, or we can just say, let's take the key factors. But what I want to show you is that this is the adjusted productivity in China, again, taking the linear portion out and then fitting an S-curve. And this shows a year 2005. And that's about, yeah, right. That's about when we see the slowdown about a decade ago, that the very fast 8+% growth that China was experiencing has more or less stopped. And you can try to produce more or do all those things, but this may be just the natural phase of the S-curve. The saturation is approaching. So that's that. And yeah, we had to do some interesting work with the numbers from China and India because they were annual growth per year. One could do a lot. And this is their, yeah, this is the average again. So again, if, eliminating time, writing productivity as a function of the average of the key infrastructure technologies, you get this curve which gives you the year 2005 again, independently. So there's two ways to test this. And then the last curve, oh, it was, is India. So in India, pretty much the same story. This is the adjusted productivity. This is the S-curve. In India, we get 2006, so it's a year later. And then eliminating time as a growth as a function of productivity, we get, oh, this is the old, you get around 60% penetration. That's the magic, where the magic occurs. You have that inflection point. So anyway, these are the two test cases we could think of. If you think of other test cases, then it will be good. The machinery is not that complex. It consists of some smoothing of data, fitting a sigmoid function, and then noting the points of inflection, and then eliminating from two curves time so that you have one against the other. So that's pretty much all I had to share. Thank you.
Any other comments, questions?
Where's your starting point for the ICT? Because that's been continuous since the 1950s, been building computers and
Yeah, I think
guys in telecommunications as well. There's no point zero from which you would fit your signal.
no, we did. So we followed Gordon, 1870 to 1970, 1875 to 1975 is his golden century. So that's where we all these technologies, whatever the penetration was, we assumed that was the saturation point. So how many US households, 150 million households, how many of them have electricity? That's the ultimate penetration. So we use that as the normalizing factor.
So for ICT, the number of households with a PC or the number of people with a smartphone.
So I think the business modeling team had some to grapple. There is, when you have substitutable technologies, the S-curve, you have to look at combined. So you have old telephony landline, which has been declining. But what has been growing is cell phones. So you actually don't see an S-curve. You see something that looks like broken, and then another thing that's broken. When you look at the combined, the S-curve shows up. So they had to resort to this kind of substitutable technology modeling. It's a little tricky. You have to know what replaced what. So landline was initially replaced by cell phones, and then now with smartphones.
Just a question about what's the penetration of internet today? Like,
how do you measure it?
Well, what is it? Because if it's like 80–90%, then we've seen the growth already. And since we haven't seen it, perhaps the guy is right that there was not a growth between 90 and 2010.
You're exactly right. The same way that penetration of electricity was not the only factor that contributed to the earlier growth.
But there was actually a late penetration of electricity which went together with all the other technologies that...
No, they are scattered. They are not all together. The average makes you think that they all grew together. But for example, the sanitation network was earlier, gas network was later. That's why I took the average.
So if you want to... Waiting for something else to happen to...
Something else, yeah, so that's the argument. Okay. If the logic is right, you're right. Just about the penetration of broadband in France is pretty high, right? And the same in the US is high. So you can't expect this to grow that much. But the argument is that one technology by itself is not the trigger to take you to the tipping point. You need this combination. Please.
Don't you think that there is maybe a difference between material objects, probably what Gordon was referring to, and the digital innovation, which consists mainly, besides facilitating the logistics, etc., into immaterial objects like everything that is produced by the digital innovation. In the end, you look at Google, they're mainly gaining money with advertisement, in the end, to sell material objects. And that maybe the first revolution, what it did, is simply to automate the production of material objects, while immaterial objects are still today produced by humans, which, there is no gain in productivity, so there are two aspects.
So you summarized Gordon very well. That's what he says. That he doesn't believe that these digital technologies have done anything. They have reduced by a huge factor time. They have saved us time in activities that we didn't care to save time. So I think kids now have watched more movies in 2015 than their age equivalents did in the year 2000. Is that a good thing? He says no. He says it's all been entertainment. There's no substance, according to him. But we have an alternative explanation that that's one leg in multiple legs that you need for this growth to occur. And the other ones being what we talked about, digital health. I mean, it's all digital. It's all to do with computer revolution, the miniaturization, electronics. That's the basis of digital. So in some sense, that's the foundation. But the way that's going to influence how productivity grows is through these, digital printing, health, transportation, etc. So, hence the impact is still to come. So, I think this is plausible. I'm not a techno-pessimist, but optimism is also another question.
And maybe sometimes the regulation, the technology is there, but the regulation is making the process slower, and finding new business models or pricing mechanisms may help to bring the technology faster to the market and make the evolution faster.
I think you have a very good point, Amira, which is this. I mean, suppose you believe this, and suppose you're a minister of something, which you may be, then what is the role of the regulator to expedite this? Actually, Rajiv has used some of these slides recently in his talk, because the argument here is that the faster you grow your communication and information infrastructure, perhaps the faster you get to this growth. So he kind of liked it, and he used some of the data here in his last speech that he gave.
Yeah, and we hear some complaints about the regulators are making the growth slower, or the deployment of technology slower sometimes.
Yeah. So if you build
new pricing, new mechanisms that satisfy all the parties may be.
Yeah, I think there's definitely if you're convinced by this, I think there is a function for policy. There is an implication how to enable. By the way, in all of these we're talking about infrastructure, which is usually large investments, not by private entities, but by governments. I don't think the electricity grid in the US grew by private enterprise. It grew because it was an enormous undertaking in terms of expenditure, but its impact on commerce was enormous, because trucks can now take one day to go from A to B, as opposed to many, many days or none at all.
And sometimes we can just eliminate the man in the middle, even if it's the government.
Yeah, so you sound like these a combination of libertarians and the left wing. Both eliminate the government, but also invest in infrastructure. But lots of interesting thoughts there, yeah.
Any other questions? Okay, thank you.
Okay, thank you.